So, okay, thank you for the kind introduction. So, you see, there's all kinds of good reasons to have this workshop here and to come to Nijmegen. We did great in terms of weather. We did great in terms of organizers. But in this talk, I want to actually go to a very old and also deep problem, which is at the core of quantum gravity research. So essentially, the two-loop counterterm is at the origin of the field. And I should say, we have been thinking about this problem for quite some time, so 7 or 8 years already, and I'm quite happy to report on results in this direction. And the results are mainly due to my Jena collaborators. So there were 2 fantastic PhD students on the project, so Benjamin Knorr and Stefan Lippold, which made this all work. So what is the story about? So you see, quantum gravity is an old field, and you might wonder, why are we not there already? And we know how to quantize a quantum field theory. We know this from particle physics. There it works extremely successful. So let's copy this idea and apply it to gravity. We know what the theory looks like at the classical level. Canonically, we can start from the Einstein-Hilbert action. And then we can apply the same quantization procedure that works for particle physics and try to quantize this action. The difference to particle physics is listed here in the second line. So if you go to this procedure, you can do a one-loop computation. You find that there are no one-loop divergences appearing on shell. But as soon as you go to a two-loop computation, you see that there is a non-trivial counterterm appearing here. So this is listed here. The C that appears in this formula is the Weil tensor. We are in 4 dimensions. There's a number which is non-zero, and you see there's a divergence 1 over epsilon multiplying this term. So why is this problematic? This term is not of the form that we had in the initial action. So we cannot absorb this divergency in our bare Newton's constant as we usually do with renormalization. This implies if we want to consistently quantize this action, we have to add a new interaction term which absorbs this divergence that we have up here. Okay, this new interaction term will introduce a new free coupling constant. And typically this is taken as a hallmark that you need an entire tower of these counter terms, 1 at every loop order, in order to absorb all the singularities that appear. So in terms of perturbative quantization, the statement is that once we start from this action, it's perturbatively non-renormalizable. We can reformulate this assessment in terms of a modern picture of renormalization. So here we start from the Einstein-Hilbert action, and then we track back the problem to the dimensionality of Newton's constant. So if you think about a renormalizable quantum field theory, the coupling constants that typically appear there have either a positive or 0 mass dimension, and this is not true for Newton's constant up here. So here we have a negative mass dimension. Then we learned that if we want to have a perturbatively renormalizable quantum field theory, there should be a so-called Gaussian fixed point corresponding to a free theory to which the RG flow flows at very high energy. Then we can apply this construction to Newton's constant up here. So we switch to dimensionless coupling constants small g, small lambda by doing a proper rescaling with a mass scale. And then we want to see how these guys change if we change the renormalization group scale. Then you see that there are 2 terms appearing in the flow equation. There is the first term, which is purely governed by the mass dimension of the coupling constant, and then there's a second term, set of terms which encode the quantum corrections. Then you see for small g, these quantum corrections are always subleading to the mass dimension term, so close to the free theory, it's this term that dominates. And then you check that if the sign here is positive, that means a theory coming with positive Newton's constant will not end up at zero coupling. It will be driven away from this fixed point. So the Gaussian fixed point is not the UV completion of this action. So this formulates the assessment that I had before in terms of this Wilsonian formulation of randomization. Okay, what does this mean in terms of quantum gravity research? Are we doomed? And the answer is no. We can still attribute an effective field theory status to gravity. And the issue of randomizability will can be countered. So as long the theory becomes randomizable if we add all types of counter terms that are admissible with the symmetries to the action. So in this framework, we can still get rid of all the divergences. And there are two observations to be made in this context. So given the smallness of the quantum gravity scale in this setup, it's very likely that we will not measure quantum gravity corrections to the Einstein-Hilbert setting. On the other hand, if we adopt this effective field theory framework, this implies that we have an infinite number of coupling constants which we have to determine experimentally. So this explains why we like randomizability. So in the end, we use randomizability in order to reduce the infinite number of free coupling constants that appear in our formulation. But the story is not about divergences. So in principle, you could get rid of these guys by introducing a minimal length scale. But then you will re-encounter the problem that we had before in terms of real physical quantities, namely scattering amplitudes. So think about two particles interacting gravitationally. Then we have the zero graviton exchange, one graviton exchange, two graviton exchange. And by dimensional analysis, you find that the ratio between the one graviton exchange and the zero graviton exchange is governed by this quantity g Newton times e squared. So it's governed by the high energy part of your theory, and the main contribution is coming from high energies. This gets worse and worse. If we include two gravitons, then this theory will diverge as the energy to the power of 4. So the main contribution also comes from the high energy behavior. So in this case, the scattering amplitudes will be dominated by your UV cutoff, even if you regularize the theory at high energies. So survey what is on the market. So we discussed the effective field theory standpoint. Then one can say, okay, this is the onset of new physics. This is taken by the string theory approach or loop quantum gravity. And in this talk, I will take the status, so maybe we can still make sense of gravity in terms of quantum field theory. And I will focus on the asymptotic safety construction. Notably, we also heard yesterday about Horava-Lifshitz. So if you want to know about the connection between the two, ask me after the talk. So asymptotic safety. So the starting point of our construction builds a little bit on effective field theory framework. So what we want to do is we want to construct a theory by specifying a field content. In our case, this will be gravitons, and by specifying the symmetries. So in this case, we will be conservative. We use coordinate transformations as symmetries. Then we construct actions from this field content, and we allow for all actions that are compatible with these symmetries. Typical example are the Einstein-Hilbert term up here. all these actions form a structure called a theory space. So we can introduce coordinates on this space. So in our case, this will be Newton's constant, the cosmological constant, and coupling constants, for example, associated with higher derivative terms. Then we can construct RG flows on this setting. This is a natural structure that appears here. So typically we have beta functions which tell us how these couplings change with energy scale. This is the cartoon version of the construction. So theory space is the space of all action functionals. RG flows are a vector field on this space. We have RG trajectories, which are the integral curves of this vector field. And a complete quantum theory is a complete RG trajectory, so it has a starting point at very high energies, and we want to flow it down to low energies, integrating out all quantum fluctuations. In order to get the UV completion in this framework, I alluded about this before, we have to rely on fixed points. So the power of the fixed point means that we can send our energy scale to infinity while keeping the dimensionless coupling constant finite. So this ensures that we don't encounter unphysical UV divergences, and we get a well-defined short distance physics. So here is the cartoon version of such a construction. We have a fixed point sitting here in the middle. The fixed point has two types of eigendirections. So there are RG trajectories which naturally flow to the fixed point at very high energies. And there are RG trajectories which are repelled if we send k goes to infinity. What we are interested in terms of renormalizability are the RG trajectories that end at the fixed point. And then you see somehow these RG trajectories span the so-called UV critical surface, and we have to pinpoint our theory on the surface. So this gives us a set of free parameters and which are not predicted by the construction. So this has to be taken as an experimental input. So see the number of experiments that we have to make in order to pinpoint our theory on the surface equals the dimension of the surface. So as long as the dimension of the surface is finite, we can do with a finite number of experiments to say where we are here. So in this sense, the construction is better than the effective field theory framework. So you get an additional selection criterion by saying you are in the UV critical surface of a fixed point. So what fixed points are on the market? We already discussed Gaussian fixed points. The prototypical example is QCD. And here we are dealing with theories that are asymptotically free. Alternatively, one can get away with so-called non-Gaussian fixed points. So here we have a theory that is interacting at high energy scales. And a prototypical example for this construction is gravity in 2 plus epsilon dimensions. So here you can rely on the epsilon expansion and prove that the corresponding non-Gaussian fixed point exists. There is to be stressed that both constructions are equally predictive, and the core of the asymptotic safety program says that this 2 plus epsilon dimensional fixed point also survives in d equals to 4 and can be used as a UV completion of gravity. So this is not all on our list. So in order to make this scenario work, we need a non-Gaussian fixed point to have a controlled UV behavior. We want to be predictive. The most simple thing to get this is have a finite dimensional UV critical surface. And in the end, we also want to connect to known low energy physics. So then we require that admissible RG trajectories flow to a region where general relativity is a good approximation. So then we can recover all the successes of GR in terms of all kinds of tests. So what's to be said about what's the status of the program? So first we need a tool in order to construct RG flows in a gravitational setting. In terms of getting explicit computations, the thing on the market is the effective average action and the flow equation for this one. So the idea is to follow the Wilsonian approach to quantum field theory. We organize our quantum fluctuations in terms of momenta, and then we integrate out quantum fluctuations shell by shell. And this gives us the RG flow that we had seen in the cartoon version. This equation here makes this precise. So the left-hand side tells us how the effective average action changes with the scale k. On the right-hand side, there is essentially one loop structure, but the appearance of the exact propagators here make this a formally exact equation. So it has the same information content as the path integral. In order to study properties of these equations, it's very important that you don't have to specify a fundamental action that you want to quantize a priori. So in a sense, this comes out by tracing the IG flow to high energies, and then you might be able to find the corresponding fundamental action associated with a fixed point. How to get solutions to this equation? So it cannot be solved exactly. So you have to go to some approximation scheme. Typically, you make an ansatz for this gamma k in terms of operators that are important to your problem. So here, schematically, we have the coupling constants multiplying operators. So this could be the Einstein-Hilbert action in the simplest case. Then we take this ansatz, we substitute it in the flow equation, we project on the set of operators retained here, and by comparing the coefficients on the left and the right-hand side, we get our beta functions. There, in terms of structure, what has been studied. So in the beginning, people were focusing on single metric fluctuations. So here we split fluctuations in a background and fluctuations around this background. And in the first stage of the exploration, we looked at the sector where the fluctuations themselves were neglected. So this is called single metric. And now there's new developments which also take the power of the fluctuation fields into account. So in a sense, here you are studying vertices which don't include the fluctuation fields, and these more elaborate computations also take vertices including the fluctuation fields into account. For the rest of the talk, I will talk about the single metric approach and focus on the terms that can appear here. So this is the cartoon chart, what has been studied. Down here we have the Einstein-Hilbert action. We have managed to get functional results in terms of f of r theories. So here we retain an infinite number of coupling constants, essentially going to r to infinity. We can include tensor structures of the C² type. And the core questions of this talk is related to this setup. So what happens if I study the Einstein-Hilbert action supplemented by the perturbative counterterm? In order to understand the story, let's recap what happens if we do not include this counterterm. So then our ansatz for the effective average action contains Newton's constant, the cosmological constant. We can substitute this ansatz in our flow equation. We project on R and the volume term, and we obtain beta functions. So this has already been done in the last century, and it was observed that there's evidence for the non-Gaussian fixed point, as we had in the scenario before. The integral curves are shown here. So you see the high energy phase of the theory is governed by the non-Gaussian fixed point. There is a crossover phenomena going down here to the Gaussian fixed point region, and classical general relativity appears here where the dimensionless Newton constant is small. So what happens if the two-loop counter term is included? Does it destroy the asymptotic safety scenario? So this question is also an old one. It was raised by Hermann Nicolai almost at the beginning of the program. So the ansatz that we want to study is this one. So we supplement Einstein-Hilbert by precisely the two-loop counter term. There's a new coupling constant appearing here, sigma, which is associated to the Weil cube term. And we introduce the corresponding dimensionless coupling constants. Then, in terms of structure, there are two surprises that come up. The first surprise is that once we add this term to the action, there's no feedback of the coupling sigma into the Einstein-Hilbert sector. Why is this the case? So here's the argument. So let's study the Gorov-Zaniotti term as it is written here. For our flow equation, we have to take the second variation of this term with respect to metric fluctuations. You see, since this contains a c cubed, there will always be a c left in this. Then you can expand your flow equations in powers of the background curvature, and the lowest order term that appears is of the form c bar. You take the trace of c bar, and since the Weil tensor is traceless, this vanishes. So there's no way that this term can feed back into a two-derivative term in your effective average action. The second surprise is that we can make a general statement about the beta function for sigma. And the statement that we can make is that this is actually a cubic in sigma. So this is also coming from purely geometric consideration. You can parameterize these beta functions in terms of these coefficients C0, C1, C2, C3. These will be a function of g and lambda. And the series stops at sigma cubed. The argument underlying this is similar to the one that I had before. Again, we study the second variation of the Gorov and Zaniotti term. It's proportional to c bar. In order to get the running of sigma, we have to extract the term which is cubic in C. That means terms that contribute to this structure can at most have a coupling which goes as sigma to the power of 3. Then our task is to actually compute the coefficients C0, C1, C2, and C3. This is the hard thing. And this was done on the computer. So we used Mathematica with the exact package. We had to crunch through 900 vertex insertions in the trace. And it took us about a month of CPU time to just get a few numbers. And you see, the result is quite pretty. So here's the complete list of these coefficients C0, C1, C2, and C3. And the important property that you are after is this coefficient C3. It turns out to be non-zero. Then you see this structure of the flow equation, the beta g, beta lambda, it's unchanged. So this sector admits a fixed point. This is what we have seen before in the diagram. But as long as you have this C3 being non-zero, this is a cubic, which means that this beta function always has a real root. Then we see that this real root provides a natural extension of the non-Gaussian fixed point that we have seen here to the space of the extended truncation space. So we recover the non-Gaussian fixed point that we have seen before, also in the presence of the Gorov and Zagnotti term. Now, what about the stability properties that are encountered in the perturbative quantization? Yeah.
Sorry, can I just ask you one thing?
Sure.
When you say that the second variation of the Gorov-Zagnotti term is proportional to C,
Yes.
that's because I thought that you would have all sorts of contractions of covariant derivatives and all.
Yes, yes, yes. It's all there.
It's also this sigma is very. Okay.
No, I truncated a tensor structure containing the C here. There's also a C squared and a C cubed, which I bunched into this order R squared. But you are only interested in the lowest order in the background curvature. And you see that if you do this precisely, then there will be 4 covariant derivatives contracted with the index structure. But in the end, these will result in contractions with the metric.
Sorry, so will you generate C square?
From this term,
Yeah.
yes. So if I have a bunch of covariant derivatives, then this will go like the heat kernel expansion. So at the lowest order, it's just a metric. Then the next order has R-type terms, and the next order has R-squared terms. But they are all always suppressed compared to this leading term where it's just the metrics appearing. Okay, we computed this one. We saw it survives. We want to check stability properties. And then we learned the following. So here's the location of this extended Gorov and Zagnotti fixed point. Lambda stars, G star are precisely at the Einstein-Hilbert. And there's a unique extension to the inclusion of the sigma coupling constant. Then we see that the new direction that appears with the sigma coupling constants is actually irrelevant. So this coupling constant at this fixed point does not introduce a new free parameter which needs to be fixed experimentally. So this is the statement here, and you see in terms of relevant operators we are dealing with 2 different fixed points, and the set of relevant operators associated with the Gaussian fixed point can be different to the set of relevant operators associated with the non-Gaussian fixed point that we have in the quantization here. So this is the important message why the arguments on perturbation theory do not directly apply to the asymptotic safety scenario. Then we also integrated the flow equations and checked that the crossover is still intact. So here you see this is the extended non-Gaussian fixed point, and you can still construct RG trajectories which have the similar property as we encountered in the Einstein-Hilbert case. So there's a crossover into the classical region, and you can recover GR down here. So everything works as we had seen in the classical Einstein-Hilbert computation. I should also stress that the non-Gaussian fixed point will solve your scattering amplitude problem. So you can redo the consideration here. You see that the scattering amplitudes are governed by the ratio Gn times E squared, and if you have a fixed point around, this goes to a finite number, G star, which means that the amplitudes, if you take the ratio, it will be proportional to G star squared. So instead of having these guys being more important than these guys, you see that for G star equal to 1, they will all get the same importance. So you stop being dominated by the high energy part. If I have 2 more minutes. 10. Okay, I'm going fast. Then let's briefly discuss this one because it's important. So up to now, we only had pure gravity. Question is what our universe is not empty. We know that there are matter fields around. So can we use the same mechanism in order to get gravity matter theories? And you see there has been a lot of work going on here. I was not directly involved, so the expert is sitting here in the audience. But let's see in terms of cartoon versions. So in the simplest case, what you can do is you can take the Einstein-Hilbert action and you can substitute, complement the theory with free non-interacting fields. So you can introduce scalar fields minimally coupled, you can introduce Dirac spinors being minimally coupled, and you can introduce gauge fields including their own gauge fixing and ghost terms. Then there's an interesting number appearing. So if you want to put the standard model of particle physics in terms of this framework, it tells us that there should be 4 scalar fields, there should be 22.5 Dirac spinors, and 12 vector fields. So this is the number that you are after. And then you can construct the beta functions of g and lambda using the same technology that we had before and see for which values of your field content you recover a similar fixed point as in the pure gravity case. So the study is here. So here I sliced to the case where you have 12 vector fields sitting around. And each dot here in the diagram marks the existence of a suitable fixed point for asymptotic safety. Then you see here's the number of scalar fields, here's the number of Dirac fields, and the standard model sits up here, so it's close to the boundary, but within the range of parameters where you get a suitable asymptotically fixed point for asymptotic safety. Of course, I should stress this is the simplest computation that you can do. There are much more elaborate things on the market, and it seems that the result that the standard model field content is compatible with asymptotic safety can also be checked in more elaborate constructions. In this simple settings, it's just 1. Each dot is exactly 1 fixed point. But you see, the Einstein-Hilbert also gives just 1 fixed point, and typically more fixed points only appear in the presence of higher operators. And since we are only doing Einstein-Hilbert here, you are not surprised to have only 1 dot. Okay. This brings me to the conclusion. So all our studies indicate that there is a non-trivial randomization group fixed point for gravity, and it serves as a good candidate for completing gravity at trans-Planckian scales. There's good indication that this fixed point is connected to a classical low energy physics by RG flows. And it's also likely that this fixed point extends to gravity matter systems. There are some results in the fields that I would still like to highlight. So we have seen this fixed point appear in a wide range of approximations. We have indications that the construction is highly predictive. And there are also new results on the market which contain the construction in d equals to 2. So here it was recently be shown that the fixed point in precisely 2 dimensions actually has all the properties of a unitary conformal field theory. In terms of matter, there are also things. So here the existence of the fixed point in the presence of the one loop counterterm was already shown 6 years ago. We have discussed that the fixed point is probably compatible with standard model matter. And then there's the paper by Shaposhnikov and Verdaguer, which used RG flows to give an estimate of the Higgs mass based on asymptotic safety. And this turns out to actually hit what has been observed experimentally. See the preprint number, so this was before the discovery of the Higgs. What is ahead of us? So given that we have these fixed points floating around, you can ask the question, do they entail a universal short distance behavior? In terms of scientific questions, you can then ask, can we construct correlation functions and critical exponents characterizing this universal short distance behavior? And more importantly, can we recover these universal short distance behaviors within different approaches? So for example, can we use a spin network to re-engineer the universality class that we have probed here using the randomization group approach? Then of course, with all quantum gravity theories, there's always the question, can we construct a connection to experimental data? And since we are here in the framework of quantum field theories and have RG flows at our disposal, this point is probably conceptually clear. You start from your non-Gaussian fixed point, you trace the RG flow to energy regimes which correspond to low energy physics, and then you can check if there's something interesting coming out at these energy scales. So with this, I would like to stop. Thank you.
We have plenty of time for questions. Flavio?
In relation to that in particular, what happens to the flow in the deep IR regime past classical gravity?
Let's see. Let's use this diagram. And it depends on the cosmological constant. So here, these RG trajectories can be completed to the deep infrared k equals to 0. This is fine. Here you encounter general relativity with 0 cosmological constant. And here, if you have theories with a positive cosmological constant, the honest answer is we don't have a good answer to this yet. So it seems that the simple Einstein-Hilbert result that I've shown here is insufficient to cover the RG flow in the very deep infrared in this case. So essentially what happens is that the trajectory here wants to take a turn and switch on other operators which are not of the Einstein-Hilbert form. If you have a good guess for what operators this could be, it wants to leave this plane.
One question, Enrique?
It seems that there are indications both for neutrino masses and also from dark matter that you need more matter than there is in the standard model. So given the fact that you are very close to the border, it seems that this fixed point is in danger if you have more matter.
Well, you can still incorporate a dark matter scalar, and you see if you look at this point, it depends on the direction or the type of matter fields that you want to add. So there is a chance that not everything works. Yeah.
Raymond?
Can I have
Sure.
a naive question just to update my knowledge of this? I've been following Lytham and also Reuters' work as you
Yes.
represented here. You mentioned at the end towards understanding the short distance behavior.
Yes.
But on the other hand, we also have seen infrared behavior being sort of deduced from it.
Mhm.
Now, when you go to the C, beyond the C squared, and I
Yeah,
notice you
yeah.
have C cubic,
Mhm.
is that going in the direction of short distance, or
No, with short distance, I just mean the theory sitting at the fixed point. So since you have many infrared theories approaching this point, this approach essentially washes out some kind of information that you see at long distances.
it washes out the
Yeah.
information for the long distance
Mhm.
behavior, right?
Yeah.
So they all converge to
Yes.
something
Mhm.
similar
Yes.
in terms of short distance
Yes.
behavior. But then the expression that you have Einstein, Hilbert,
Mhm.
and then the R squared type, and
Yeah.
then you now have R cubic,
Yes.
including C squared,
Mhm.
about cubic term.
Mhm.
That would lead you to a shorter distance, or what? I'm just trying to see the overall.
No. In terms of the monomials that I had, these are purely ordering devices. So in essence, what you are interested in is the beta functions. So these guys carry the information about the fixed point, and the geometric quantities like the C cubed are only used to identify a certain set of beta functions.
Okay.
So we have never used solutions of equations of motion in this program.
Okay, so you start with ultraviolet.
Yeah.
And run down.
Yeah.
In energy scale. Another attached question is, as you know, Woodard and Thomas have been working on two graviton for the longest time.
Mhm.
What is your comment on their whole program? Rich is not here, so.
We can discuss over coffee. Is it okay?
I see. Okay.
Jan has another question.
Sure.
So in this nice figure you have there, yeah. So how are typical grand unified models doing? So this act, I mean the red mark is the standard model, I guess.
The red mark is precisely the standard model.
Yeah. So how are grand unified models based? Like
Do you want to comment? Since you have studied this question.
What happens here is that too many scalars or too many near fermions go against asymptotic safety, but gauge fields work in favor.
Mhm.
So in grand unified theories, you would say you have bigger gauge groups, and so that helps. But then you have too many scalars, typically, in order to break it, and so they fall out of this domain.
so typically they will fall out of this.
Yeah. I should also say, maybe in comment on the previous question, is that here there is room to add a couple more
Yep.
degrees of freedom, like right-handed neutrinos
Mhm.
and a few scalars. But it should also be said that there's a large theoretical.
There's an error bound on this boundary.
So
Yeah.
one shouldn't really try to make too much.
Any other question?
Fair statement.
Enrique?
I have maybe a naive question. I'm not an expert, but I've seen these graphs of A theorem in QFT in which you have the flow going from the IR to the UV, and they
Mhm.
say it can't go into this cyclic kind of behavior there. Can you show the picture of this?
Yeah, but it's not a limit cycle that I'm showing here.
Not a limit cycle.
So it's just spiraling into the fixed point. So typically, if you have these A theorem graphs, you would have an extended region like an RG trajectory which closes and has a non-trivial length.
Thank you for the organizers for giving me the opportunity to be in this nice meeting. So, okay, this is the title. And this is the outline, but somebody said I never wrote an outline, and maybe I always write an outline. Maybe I should skip it. So let me go for this drawing. So, well, quantum corrections to Newtonian potential goes back quite a long time. Already Schwinger and had thought and had written about this, and Radkowski made the first calculation in using graviton change. Okay, and later this was taken out by Donoghue in order to test effective field theory description of quantum gravity, in the sense that he saw that these corrections are necessary consequences of quantum gravity independently of the high energy completion of the theory. Okay, so later this was already used by Duff, Liu, and Garriga Tanaka to prove the pictures that emerge from the anti-de Sitter conformal field theory correspondence and the Randall-Sundrum brane world scenario. So they computed, in fact, the correction to the Newtonian potential on a brane in anti-de Sitter in 5 dimensions, and they found agreement with the quantum calculations that had been done previously. The corrections to the Newtonian potentials are always given by this kind of term, Planck length divided by r to the square. Planck length square is just the gravitational constant. And A is a coefficient that depends on the kind of matter loops, or loops, of matter that one uses. It has been done for scale, spinors, and vector fields, and also for gravitons. Although for gravitons there is no consensus on what is the value of A as far as I know. Okay. So the methods of computation are essentially two methods. The first methods that were used are just the analog of the methods that one used in QED. That is to say, to obtain the potential from the non-relativistic limit of scattering amplitude of two heavy particles at rest by graviton exchange. So this is similar as one finds corrections to the Coulomb potential due to the photon exchange of charges. But the second method is using effective field equations for metric perturbation. So in that case, what one does is first, one computes the graviton self-energy up to the one loop order, usually, on the matter that one is trying to consider, and then compute the gravitational response to a point source, to a massive point source. Okay, this is already in 75 for Duff did this, and then Parr-Woodard had emphasized this quite a lot. So in this second method, using effective field methods, the method has an advantage that it can be used not just in flat space, but in any kind of background space-time, in particular in the Sitter, where scattering amplitudes may not even be well defined. And also the equations, in order to get real and causal field equations, one needs to use the Schwinger-Keldysh in or closed time path, the same names, well, different names for the same thing. And this was emphasized by Parr-Woodard also. All this thing, I mean, this calculation is in a set of program in order to prove or to test perturbative quantum field theory in the Sitter space-time, and that goes beyond the three-level approximation. Okay? Well, the strategy that we'll use is we fix point mass in the Poincare patch of the Sitter. I'll explain why we use this Poincare patch, and then we derive and solve the field equations from the closed time path and normalized effective action for metric perturbations coupled to quantum matter. We'll use the large N approximation in the sense that we'll couple the gravitational field to N, where N is a large number of massless conformal couple fields. Okay? And as a technical thing, we will, in the Poincare patch, we'll separate the metric perturbations into scalar, vector, and tensor perturbations. This turns out to be quite useful in order to simplify the problem. And also, it's important that we define the Sitter invariant initial vacuum, which is a generalization of the Banach-Davis vacuum for the interacting vacuum of the gravity with the matter fields. Okay?
Excuse me,
Yes.
totally ignoramus question. What is the Poincare patch?
Poincare patch is the specially flat slice. I mean, yes, in the Sitter. Okay, in quantum field theory, usually one is interested in in-out transition elements, and one defines usually the generating function, the in-out generating functional, which in a path integral representation, where phi means the field that we are considering, J is a source field, classical source that couples to this field, and this is the path integral that generates, this path integral generates essentially or gives time-ordered in-out transition elements. And from this generating function, one derives the time-ordered operators, field operators, and from this, one may derive, well, from the Fourier, the Legendre transforming the W, which is the log of the generating function, one may define the effective action for this transition element of the field phi. Okay, but in the in-out, in the in formalism, we essentially do the same thing, but we have to double the number of degrees of freedom, because we are interested in expectation values of operators. Okay, this is in cosmology. It is usually one is interested not in matrix elements, but in true expectation values of correlators, and so one needs to impose initial conditions at some early times rather than boundary conditions at initial and final times. So for that reason, if one introduces here the completeness relation, where alpha t are just eigenstates of the field operator 5 at some future time t, capital T is just some future time that is larger than the time of interest in which we are doing our computations, then this thing just becomes, in the integral representation, is just we have two integrals with two fields, 5. One is 5 plus and the other is with 5 minus. 5 plus is with an action which corresponds to the action for the field that advances in time to the future. And then we have another field 5 minus that it corresponds to with the action, which is the complex conjugation of the previous one, and it corresponds to a field that goes back in time. The generating function one can define in that case. It depends on two different sources, and so this is a generalization of the previous case, and where one has to take the condition that the 5 and minus fields agree at this capital T. Okay, so they take the same value 5t at capital T. Okay, so therefore we have two sources and we have two fields, and this can be represented in this path this closed time path kind of thing, which it essentially tells that the 5 fields evolve in time, forward in time, up to this capital time t, and then the minus fields evolve backwards in time and with this capital T and with the complex conjugation of the action here. And instead of time-ordered elements, what one finds from the generating functional, one finds path-ordered elements. For instance, if the path order corresponding to plus fields is just time-ordered, but the path order of minus fields corresponds to anti-time order. Okay, and of course the effective action then depends also on two fields, and it's just the Legendre transform of this the log of the generating function. Okay, so this is just a small review. Now about the initial vacuum. Well, in flat space, we are usually, in order to define the interacting vacuum of the theory in a time-independent Hamiltonian, what we do is to tilt the time with some small I epsilon prescription, and so we tilt the time to a complex time, and and what this does is that if we start with the initial time infinity in the past with some free, the vacuum of the free theory, then this thing generates the vacuum of the interacting theory forward in time, which is the vacuum which corresponds to the state of least energy that we have. Of course, in time-dependent Hamiltonians, this in general is not the case, except in some cases. Namely, when the free fields in the far past have an oscillating behavior, which is similar to the oscillating behavior that they have in Minkowski spacetime. In that case, one still is able to define an adiabatic vacuum. Initially, adiabatic vacuum of the interacting theory. Now, in this closed time path, of course, now we have two times: the past time and the t plus time that corresponds to the path that goes forward in time, and the t minus that corresponds to. And because the action, remember, it was just a complex conjugation, so this means that this prescription is now it has these two plus and minus I epsilon here, and so in order to we have to take this into account. Now, in the Poincare patch, which is partially flat patch of the sitter, this is what this guarantees that this behavior of the modes is the same as the behavior in Minkowski spacetime, and therefore, if you use this in Poincare patch, we will get the interacting vacuum of the theory. Okay. Now let's write the interaction of now. Well, as in the previous talk, we know that quantum gravity, perturbative quantum gravity, is not a normalizable theory, but it's still okay if we treat this as an effective field theory, in which the quantum phenomena are characterized by some scale which is larger than some cutoff scale. Cutoff scale is LP, which is Planck length, essentially, which is the square root of the gravitational constants. That we'll write this as kappa. And so the effect of the high energy modes on the low Lagrangian, low energy Lagrangian is given in terms of derivatives and powers of the curvature to some given order in LP over L. So we find corrections that go with this thing to some order, and okay. So this is how this effective field theory of quantum gravity works more. Now, we'll assume the metric perturbation, the metric will be G tilde, which is just some background metric. It could be flat space, but in general, some background metric plus a perturbation that we are going to quantize. Okay. For the matter action, we will write the matter action expanding in terms of h, and we'll end up at h squared because for our purposes it will be enough. So this includes, of course, the stress energy tensor and then a correction to this of the matter field. Okay. Now, for the gravitational action, of course we need to have the Einstein-Hilbert term. And we have to include counterterms, or we have to include, using this effective field theory approach, terms with higher curvature. For our purposes, we only need these terms to curvature of square terms in the curvature. So in 4 dimensions, there are only 2 extra terms. This term is essentially, in 4 dimensions, this is just the Weyl square of the Riemann, so the Weyl square term, and this term is just the square term. So A1 and A2 are some free parameters that have to be determined by experiments. At this point, they are, since we are going to use dimensional regularization, this is just some bare parameters together with the cosmological constant, with kappa. And since we are going to use the Largian approximation, we will redefine a gravitational constant k bar, which is kept fixed, and which is just k squared by n. So in this approximation, now the fundamental cutoff scale of the theory is just kappa squared instead of kappa, which is the Planck length, which is the one that is measured by Cavendish type experiments. Okay. Just notice that from here, if we assume, well, remember that G tilde is G plus perturbation, metric perturbation. So if we expand this in terms of the metric perturbations, notice that the graviton propagated goes like 1 over n. And if we include in this graviton propagated, we include a graviton loop, this term goes like 1 over n squared, because graviton loop includes 4 propagators, so that means 1 over n to the 4. But there are 2 vertices, which goes like n squared, so the whole thing goes like 1 over n to the 4. Whereas the matter loops go like 1 over n only, because that includes 2 matter loop includes 2 propagators that goes like 1 over n squared. But since we have n fields, we have multiplied by n, and we just have 1 over n. So we avoid using graviton loops by, in a consistent way by using this Largian approximation. And now the generating functional, of course, now we have 2 fields, the gravitational field, metric perturbation, and 5, and it has an aspect like this. We can, if we assume that some density matrix factorizes at some initial time, then we can integrate the matter degrees of freedom, and we get something like this, where the result of this integral is given in terms of e to the sigma, I sigma. Okay, and if since we are not considering matter loops, we can keep this only to up h squared. So this is a quadratic action, and for a quadratic action, it can be shown that the effective action in that case is just given by this expression, where now the g's plus and minus are substituted by the expectation values of the metric perturbations in the in vacuum that we are in the interacting in vacuum that we are considering. Then the field equations are derived. Field equations for the metric perturbations, or for the expectation value of the metric perturbations, are derived from the effective action by this equation. Okay. Now, the effective action in general will have this term. It will have, of course, since this sigma term includes matter loops, there will be some ultraviolet divergences that will be regularized by the counterterms. Okay, and and then after regularization, one renormalizes the thing, and one has a renormalized gravitational part, which of course includes plus and minus fields. And then this is the renormalized action. This thing up to h squared is given by a term that just is not I mean, it factorizes out from the, which is independent of the metric perturbation. It factorizes out from the effect from the generating functional. And then we have a term linear in H. This term, when we put this to 0, this is what defines the semi-classical background. So the semi-classical background meaning essentially Einstein equations with the expectation value on the background of the stress energy tensor on the background. So this comes from equating this thing to 0. And we'll end up with an action that is quadratic in the metric perturbations that has, in general, for coupling with some matter fields, it has this kind of expression. A term which is essentially of the Einstein that comes, it's a quadratic term that comes from the Einstein-Hilbert term, and then terms whether this thing that is expectation value. This means expectation value for the matter fields in its initial vacuum state. And that is the most important term and the most non-trivial is the one that it is given by the path ordered of stress energy correlators, the stress energy of the matter fields correlators in the connected part of this. Okay? So this term is responsible for most of the non-local properties that we will encounter. Okay? For conformal fields, we simply assume a mass scalar field, phi tilde, conformal coupled. Since I'm using dimensional regularization, I use this n is principal arbitrary, so this is coupling for this thing. And in this case, actually, the normalization, when we use dimensional regularization, only one of the three of the bare parameters needs normalization, namely the one that it has this coefficient A1, which is the one that appears with the Weil square term in the action. Okay, and so this bare term has to be substituted by this normalized thing, which depends on some scale mu. Mu is some normalization scale, arbitrary scale, and so this is the type of divergence that we have. B is just given for the scalar field is something that is given by this. Okay. Of course, this thing, the action is independent of the normalization scale, so it means that this if we change the scale, the normalization coefficient mu changes in this form. For in order to simplify somewhat our calculations, we'll use a mu bar scale. We'll fix mu bar so that this term, which is, remember, is the coefficient that comes in front of the Weil square term in the quadratic term of the action, of the gravitational action, is 0. Okay, but at the end we'll substitute for arbitrary thing. The effective action for the scalar field was already computed some years back, but we want to give an expression for the general conformal field theory, not just scalar field, but any other field, and also for even for strong interacting fields. And for that is quite easy. In fact, if you use that the counter terms for any conformal field theory was already found by Duff in 1977, and it is given by this in dimensional regularization, where C squared is the Weil square term, and E4 is the Euler density in 4 dimensions, and B and B prime depend on the matter content. For instance, for free fields, this is the expression. If we have just massless and zero massless fields, n 1/2 is the number of massless spinors, and for vector fields, and 1 is the number of massless fields. Okay, but B and B prime are B and B prime usually are in the literature in conformal field theory are usually called A and C. B prime is A essentially, and B is C. But we reserve A for the scale factor, so We cannot use, so we use this B and B prime. Okay. Now, under conformal transformation, of course, the matter action doesn't change. The conformal transformation means that the G mu nu changes from G mu nu to G mu tilde by this form, and the phi bar, so we define a new phi, which is phi bar by this expression. So this thing doesn't change, and so this means that the unrenormalized sigma also doesn't change. However, the difference, these counterterms change. I mean, they give finite contributions at the n equal when n tends to 4, and so therefore all we have to do is essentially we use the results that we already found for one scalar field or n scalar fields, and then make this computation in order to find the general expression for any conformal field theory. Okay. Well, of course, we have to put at some point, we have to put point source. Point source will be a particle of mass m, and this is, of course, the action for the point source, which this is the normalized for velocity of the source. And now we are going to use this, I mean, the metric will be written in that form instead of the form that I had previously. So this will be A is a scale, is a conformal, well, conformal factor of the metric, and this metric is just flat metric plus metric perturbations. And the effective action will, of course, now will be written in terms of G, this new G tilde, which is separated in this form. And we, in order to add this source, we can add just the source by hand, and so we put, so I define S log as the gravitational action that I had given before, and I put this extra classical source that will generate a classical field. Okay. The final action that we found for the general conformal field theory, it has this kind of expression. This is the effective action is given by these terms, but I haven't written all the terms. But essentially, you see here this beta is the term that is an arbitrary parameter that comes from this. Essentially, it is related to the R squared term in the action, in the square part of the action. B and B prime are the terms that come from the trace anomaly and depend on the matter content. And of course, this is the Weyl tensor for the plus and minus fields, and these are some kernels that at that moment we don't need to specify what their value is, because for the field equations we only need a combination of these terms. Now, for the metric perturbations, so since our metric will have this form, so it's especially flat Friedman-Rousseau metric, A at that moment is still unspecified, and so the metric has this form, and we can separate into scalar, vector, and tensor modes according to the properties of the metric, how it behaves under spatial rotations and translations in the flat section. Okay, as usually people do in cosmology. Because in general we have two, for scalars, we have two transverse vectors, that means 4 degrees of freedom, and a traceless and transverse tensor, which it also has 2 degrees of freedom. However, it is convenient to use as many gauge invariant degrees of freedom as one can, and in fact, one may construct from these objects, one may construct 2 scalar degrees of freedom that do not change under coordinate transformations, 1 vector, transverse vector that has 2 degrees of freedom that doesn't change under this. The tensorial part of the perturbation doesn't change under gauge transformations. And then there are 4 degrees of freedom that can be written in terms of a vector with properties, with transformation properties, which are like this, where under infinitesimal transformations is just this same psi is just. So this x mu has a very simple way of changing. So the metric in general can be written as a gauge invariant part, in that sense, and in the sense that I mentioned, with those two scalars. Actually, these two scalars are the so-called Bardeen potentials, a transverse vector and this TT tensor part. And then this is the Lie derivative of with respect to x, with this vector x. Okay. Now I have to specify a little bit more what I mean by this action with the particle, the point particle. So we'll fix at the origin of this Poincare patch. We'll fix the particle, and we'll put the particle rest there. And this particle will not be will not react under metric perturbations. It will be just the source of classical field. Okay. So for that reason, we only need to write SP in that form. So with the we'll couple this stress energy tensor to H00. Notice that to H mu, but notice that this is just T00, and H00 can be written in terms of these Bardeen potentials and this extra and this X field, but this this term is just time derivative, so it does not affect. So we can neglect this term because it will not affect the field derivative. So in fact, the matter, the point source, just couples to one of the Bardeen potentials. So since the scalar, vector, and tensor sectors are independent in this linear order, we can ignore the vector and tensor parts, and we just have to concentrate on the scalar part. But the scalar part essentially has two Bardeen potentials. We have to only consider, to concentrate on the effect of these two Bardeen things. Well, here A is already we have already solved the equation for the semi-classical equation. And A is just given by the Sitter solution. Remember that we had a cosmological constant, so the H thing is just the cosmological constant. And we have a correction due to the quantum effects, because the way we have split the metric. So there is the A also has corrections here. So this is a self-consistent solution. So the Sitter is a self-consistent solution of the background equations. Now, since we have to concentrate only on the scalar sectors, I just write the scalar sector of the theory, and which depends on this. This is the term, the coupling with the massive particle, the point source, and these are Bardeen potentials. With, okay, and so the term that goes like 1 over k squared here is the term that comes from the interacting, from the Einstein-Hilbert part, and then the term that it's independent of kappa squared is the term that comes from the vacuum polarization effects, and the non-local part of the action, which involves these kernels, k and k plus minus, is given by this. So this action is actually written in terms of gauge invariant variables only. So this is a gauge invariant. Yes. 5 minutes. Okay, perfect. Okay, now we have the effective action, so we have to solve the effect. We have to find the field equations. Now, field equations are written. Remember, now we have just two potentials, the two Bardeen potentials, and so we have for one of the Bardeen potentials we have this. This is the source, the matter source, and so we have a classical term, and then which is the term that does not involve kappa now in this equation. And then we have this kappa squared term, where S1 is a rather complicated thing because this is a term that is non-local. And this non-local term actually is this H. Now, we have now a new kernel, H, which is a combination of the K and K plus that I didn't specify the previous time. The Fourier transform, this H is as the Fourier transform in a space of this expression, where this expression has to be considered as a limit in epsilon, when epsilon goes to 0 in the distributional sense. Okay. Notice that this action is local, and so this contribution is non-local, and it only it has contributions of in the past of eta. So, okay. So because of this term, so it's a causal equation. Now, we split the Verdin potentials into classical and quantum part. In quantum part, we put this k squared here. And so, and then we have equations for the classical part and for the quantum part, where this quantum part contains this S1 term, which is which includes this non-local thing. For the classical contribution, well, we just get what one will expect. So it's just the potential is just the gravitational constant divided by the usual potential, where AR is just the physical distance. Physical distance means that R is a comoving scale and radius in that case, and A is the scale factor of the matter, which is the Sitter term. So for time-independent equal time hypersurfaces, this term is, of course, independent, and it goes like 1 independent of time, and it goes like 1 over R. So this means that the gravitational potential does not change, classically does not change, due to the fact that we are in an expanding universe. Now, the quantum contribution, remember it was written in terms of these S1 terms and S2, and the difficult part here is this non-local term, because in this integral we need the full action, we need the field from the initial time up to the time that we want to compute this thing. And so we have to compute this non-local term. This is the only complicated thing here, but we managed to find this expression. And here we had to, just a matter of detail, but we had to take into account that we're using an interacting vacuum for the expectation value of the gravitational field. So we had to go back and to use properly the I epsilon prescriptions, and this translated into essentially into the change of this kernel H by this expression. This E tilde is just the well, it corresponds to the I epsilon prescription that I introduced initially. And this is the final result. But the final result depends, for the quantum contribution, it depends on this AR, all this AR, but I will discuss it a little bit later. So, flat space limit, we obtain what already people have obtained. This is just a check of the theory. For instance, just for free fields, non-interacting fields, scalar, and so on, we had this expression that agrees with what everybody finds. And now this is the final result for in the Sitter. Essentially, we have the gravitational potential. I'm writing this. RG is just the gravitational, well, the Schwarzschild radius. So this can be written. The Newtonian potential can be written always like the Schwarzschild radius divided by R, and then LP are the Planck length things. So we have this. This is the term that one gets in flat space usually. But then this is the new terms that we get in the Sitter. There are some terms such as constant. This beta and C are arbitrary. Now I have recovered C mu. C mu is just an arbitrary the normalization C, the normalized value of C, which depends on some arbitrary scale mu. So we have two arbitrary parameters here. In fact, if one could check, one could experience with these potentials, one could from here determine, from these two things, determine the values of B or C. But okay, this term is a small term. It depends on LP squared H squared. And this term is the one that in principle is potentially more interesting, because this goes like, it grows like R tilde. R tilde is just this physical distance, which corresponds to the physical distance in the flat space hypersurface, equal time hypersurfaces. So we have the small correction that find in flat space. We have this. This dependence is not found in the flat space limit. The dependence on these parameters of the square of the square terms, curvature square terms in the action. But here we found this dependence, and then there is this log AR dependence. that in principle, of course, if the distance, if you consider very large distance, this term could be large. However, this, of course, we interpret this as an artifact of perturbation theory. So this is we believe it is similar to the infrared growth of loop corrections in massless fields in lambda phi 4 theory, where these log terms can be resummed in some way, like Starobinsky did. And so we rather we prefer to interpret this term thing like as some perturbative term that we only have, that must be, of course, much smaller than 1. And then, so what this term gives into the gravitational is just into the gravitational potential is just a different power law on the gravitational potential. It is interesting that this term is always positive. So that means it's always positive because this B, which is in principle, it depends on the kind of field theory that one considers. Osborn proved that in any conformal field theory, this B is always positive. Okay? And so this means that this term, it may be always seen as a shielding of the gravitational attraction due to the quantum corrections at large distances. Okay? We had this symmetry in our, because this R term is, has this symmetry, this scale symmetry, which is this is a part of the in the Poincare patch. This is a symmetry that is obvious in these coordinates. And well, we have compared this with recently Bang and Buder did similar calculations for photons. Of course, our case, since it's a conformal field theory, general conformal theory, includes photons. And when we compare the results, we disagree with some of the finite terms, but we agree essentially with the behavior of this log term, which is important. We believe that this is due to the fact that they use a different initial vacuum, although it is difficult to compare our two methods. And okay, and that is the end. Well, there is this problem of the log AR terms that we need non-perturbative way of resumming these log terms. Of course, it will be nice to include graviton loops, but we need some different differential Diffie invariant observables, and we don't know how to make them. And it is also, it will be interesting to extend to other fields like minimal coupled fields. Minimal coupled fields have interesting, massless minimal coupled fields are particularly interesting in cosmology, in inflation. And of course, one could now also use a non-trivial check of the ADS-CFT by correspondence by using to do calculation on of the gravitational potential, classical gravitational potential, on de Sitter brane in anti-de Sitter in 5 dimensions. Also, one might try to compute the corrections with the test spinning particles. That will, this at large distances, this is it gives the gravitational potential of the gravitational potential of spinning particles, the gravitational potential of the Kerr metric, essentially. And the interesting thing here is that also this couples to vector perturbations. Okay, that's all. Thank you. Yes.
You gave two different definitions of the potential. In cases in which they are both applicable, do they coincide always?
Two different, you mean, no, you use the...
Definitions based on the effective action and on the correlator.
Ah, yeah. Yeah.
When they are both applicable, the result is the same.
They are the same. Yeah. When we consider the interacting of two static masses interacting with graviton exchange, they in this graviton you can put loops and so on. They gave this, yeah, they gave them exactly the same result. Yes. Well, for the graviton, one could use this technique. Then it will be. Then we will have to integrate over the graviton loops. Okay. This will be more complicated, but also the problem with this is that we don't know how to define a gauge, because then all the gauge invariance is broken. If we have nonlinear interaction of metric perturbations, which is what we have with graviton loops, then all the gauge invariance is broken, and this is more complicated. And in fact, people, for instance, Donahue and collaborators have done these calculations for interacting with the graviton loops, and they found many different results. So so there is no agreement in that case, because we don't have gauge invariance is always a problem here. So.
More questions? Okay, I have a question. Concerning the case with minimally coupled fields, is it too complicated to compute it? In comparison?
Well, it is more complicated because for conformal field, one can essentially one can do the calculation in flat spacetimes with perturbations and then make a conformal transformation. Essentially, one may find analytic effective action. For minimal coupled field, we have some results, but it's more complicated. It's not so easy to. Yeah.
And measure these effects.
Woodard and collaborators have done this for massless, but we seem to disagree with them with the results in general.
Just the coefficients.
Yeah.
The term structures.
Yeah, that's right.
All right, if there are no more questions, then let's thank Enrique again.
Yes, please.
This is already on. So.
Thank you. What's in this one? Sorry. It's the same name. Huh? Oops. Yes. I think so.
Okay, our next speaker is Henrique Gomes.
That's me.
He comes from Perimeter Institute in Waterloo, Canada, where he is a postdoc there in the quantum gravity group. In the past, he worked a lot in spin phones, in particular in the asymptotics of the spin phone amplitudes, and the semi-classical limit. But later, he switched to shape dynamics. And he has worked, I think, in many different aspects. For example, Poincare invariance in shape dynamics, Lorentz invariance, black hole solutions. But he's worried about the quantization of the field, I guess. And today, I hope he's going to tell us about how to deal with quantization of gravity and how to deal with evolution in a timeless framework.
Yes.
So,
Okay. Thank you, Marcel.
I don't know how to do it.
Huh.
I don't know how to fine tune that.
Yeah, you're right. It's a bit.
It's a bit, I can try to
Resolution.
but, I can try this one, but I don't think this one is better. I don't know what else I can do. I'm not an expert.
Oh, it's better.
But this is the one I will use. Can you?
It's smaller.
Ah.
What?
Ah. Yeah. Well, I'm glad I helped.
Wait. Oh no. Close your eyes, everybody.
Just slideshow and put it on pause. Slideshow again.
I have no idea.
Can
Slideshow towards bottom. Yeah. Then press pause.
yes.
Remove the cursor from that side.
Okay. I think now it's not gonna work. Well, what? Yeah, it's okay. It's more convenient for you, a little bit less for me, but I think it evens out. Okay, so I'm not gonna use this. So I'm not going to talk what was originally in the program. We'll talk about that. I'm going to talk about something slightly more, well, some aspects that are slightly more controversial about timeless quantum mechanics in configuration space. But I'm ahead of myself. First, I should have thanked the organizers for inviting me. It's really a pleasure to be here and be able to talk to so many people that are interested in this. Okay, so let me jump to it because I have a lot to cover. I'll have 3 parts of the talk. First, I will talk about certain issues that could be seen to arise when you try to put time, gravity, and quantum mechanics together. And then I will propose a particular venue of solution for that in part 2, in which I will talk about these laws of the instant. And then in part 3, which is a little bit more speculative, I will talk about how to do physics in a timeless framework, much like Julian proposed many years ago. Okay, so first let me start with this, I think, beautiful formulation, because it's so succinct and yet conveyed so much information that Wheeler had, and he was very good with these aphorisms, as we all know. And, well, space-time tells matter how to move, and matter tells space-time how to curve. And then you have the other, or another very important part of general relativity, which is that you can use space-time diffeomorphisms along a geodesic, for example, to perceive motion as if you were in Minkowski space, to a first approximation. And this is, indeed, these are very beautiful principles and theory. And Landau said in his book, he says, oh, this might be the most beautiful theory we have yet produced. But as we've been seeing over and over here, does it really need to be a fundamental theory? Shouldn't it emerge somehow, dynamically, or an RG flow from a UV theory or some other means? And if so, what aspects of it should survive, right? This is a question that I want to propose here. So usually people will respond to this and say, well, space-time diffeomorphisms or covariance should be something that survives. And so let's look at some things that might go wrong when you do try to put in the general relativistic time together with quantum mechanics. So the first thing is when you try to put quantum mechanics in a curved space-time picture, if you don't have time, so I will try to put usually some heuristic slides and then a more technical explanation, just so to guide the discussion a little. And heuristically, if you don't have time-like killing vector fields, you can't really separate positive and negative frequencies, so you don't really know what is the meaning of a vacuum that you have there. What is it that your creation operators are creating if there is no intrinsic meaning to positive and negative frequencies? And this is it's just a formalization of that concept. And you have some self-adjoint operator, and you can just integrate by parts. Here you're going to get some boundary term that will define you what an inner product is, that you can translate, choose different Cauchy surfaces. And you have some orthonormal solutions for this field equations. And if you have a global killing vector field, then you can actually also choose eigenvectors or eigenfunctions of the d derivative by the Killing, and you can separate positive and negative frequencies, and then you will have a vacuum with nice properties, and the problem here is, of course, if you don't have Killing vector fields, it's kind of at least the general consensus. So most of these things that I'm going to propose here in this first section, there are proposals of how to avoid them, but I just want to say that most of these things are not completely uncontroversial, or might be some discussion on each one. The next obstacle that one might see in joining general relativistic time with quantum mechanics comes from this, well, at least from what I understand, comes from this work of Wald and Lee in the 90s. Well, probably it comes from before that, but this is the formulation that I'm going to use here. So they propose, they have this standard, very nice way with the covariant symplectic formalism of projecting a local space-time Lagrangian symmetry to constraints in phase space once you're given a Cauchy surface. And for general relativity, what they show is that non-spatial diffeomorphisms, or diffeomorphisms that will not just keep your surface foliation preserving in a way, you can only actually project these local symmetries of space-time to constraints in phase space if you restrict the whole Lagrangian fields theory space to fields or to space-time metrics that satisfies the Einstein field equations. Okay. Okay. The problem here is this: is that, for instance, if you would do, or the possible problem, I'm not saying this is insurmountable, but the problem here is that if you do a path integral for a Lagrangian field theory for space-time, you are not just summing over space-times that satisfies the equations of motion, right? You're summing over all types of space-times, and you're summing over and in the Hamiltonian ones, these, as I said before, the ones that change the foliation, basically, they will only project to symmetries of the Hamiltonian if you take them to satisfy the equations of motion. So let me just show this a little bit more specifically, what I mean. So here, let's this F be the space-time field space, and this is my Lagrangian density. Then I'll have a one-parameter family of fields. These are just general fields, okay, that I have on this field space. These are the space-time fields, or the Lagrangian fields. And then I'll have a variation. This is interpreted as a vector field in field space. And when I vary the Lagrangian density, I will have the Euler-Lagrange equations here. It's a vector field here. And I'll have some symplectic, presymplectic one form. And the equations of motion are satisfied. And given a Cauchy surface, I can actually define a one form on field space. You see, it acts on vector fields in field space and gives me a real number, because I have this normal here, and I have chosen a Cauchy surface. And then I can use basically just the exterior derivative in field space for field variations. And I can define a symplectic form. And then I can see that the symplectic form has some null directions, some degenerate directions. And you project down. This is spelled out nicely in that paper. And then you can also look at what happens with local symmetries in this Lagrangian field space. What happens when I project them down to a phase space that I construct? And and then you have the question: can you always represent them as flows on some constraint manifold? And the answer is that for non-spatial diffeomorphisms in general relativity, only if I were to restrict this projection to a subspace of the whole field space, which is a solution subspace. Okay, and this is related to the fact that we know that in GR, the Hamiltonian is pure constraint. So, of course, if you're satisfying the constraint everywhere, you could also think of this as generating evolution. So it's hard to say. And in fact, I mean, as far as I understand, it hasn't been shown that a Hamiltonian path integral would be equal to a Lagrangian path integral. If you have in 2 plus 1, for example, and you integrate over positive and negative lapses, then you can have the equivalence between the two. But in the full 3 plus 1, as far as I understand, it is not known. Okay, so this might be one issue. This is not working. So, and another one, another thing that one might consider is this. So let's think about the transfer matrix between two boundary geometries, okay, the slabs. And so this is just a definition of what HI is. And what I have been saying before is that if I have these on-shell refoliations, they will shift these boundary geometries in a field or space-time field-dependent manner, right? And one of the aims that I will have here is to have this transfer matrix acting on gauge invariant in and out states. Okay, this is one of the things that I want to propose of how to do here, to have actually this H1 and H2 be represented by orbits that act intrinsically. And then the last point here. First, I should make it clear that I think asymptotic safety is probably the nicest approach to quantum gravity. I really like it. I think it's the one with the minimal assumptions, and it's really nice. But so don't take this the wrong way. But so as we saw in the talk by Frank, much better. And there's actually, I didn't steal this from you, Frank, the picture, but we're using the same picture, but it's a very yeah, exactly. Well, you were better than me that you should at least put the reference here. I didn't even bother with that. But so again, the RG flow in theory space is characterized by the field content and the field symmetry, above all. And it defines a theory with a finite number of relevant directions. That's the non-Gaussian fixed point. So I'm not challenging this. I think this will survive in any, or at least this approach has to survive in any attempt at quantum gravity. But what I might be challenging is if we're using the right field space and the right symmetry content. So this is one of the main points of my talk, in fact. And whether we can get around limitations that are posed when you do change the field space and symmetry content. Okay, so another issue that maybe this is just me, so maybe there are better answers out there from the asymptotic safety people, but I at least couldn't find a good answer about what happens about unitarity. There's something about these poltergeists that the non-unitary poles run faster than the scaling, but I don't really understand that to talk too much about that. But there are certain issues that I just want to distinguish between, yes, gravity has a problem of non-renormalizability, but that's not the only problem. You still need somehow you can have other sicknesses of the theory that there might be other tools better suited to approach. So for example, via gravity is still renormalizable, but it's not unitary. Okay. All right, I'm doing good time, I think. So, okay. So let's now move to what I mean by the laws of the instant. So at a heuristic level, what this problem of unitarity that I'm trying to describe is that without a fixed definition of time, right, or an a priori distinction between past and future, it's hard to impose a causality or interpret probabilities in quantum mechanics if you don't have a fixed one. And here there's just a picture that some philosophers use about different conceptions of time that you can have. You can have this presentism, which only takes a present, basically. This is like Parmenidean, or that he doesn't really believe in, that he thinks that this distinction between past futures is really an illusion. And yeah, there are some really nice quotes also. Anyways, it doesn't matter. But possibilism, so that the past and present exist. Eternalism, which is a block universe which everything already exists and is given there once and for all. I recently heard actually that there's now someone filled in the gap for the last remaining one, which only the present and the future exists, and the present eats up into the future. But they didn't have it in this picture. Okay. So let's go again to that picture that I had before. I have this transfer matrix between the two geometries, or the two metrics here. As I said before, the refoliations will define an equivalence relation between two of them if they're connected by an extremal field history, okay, or one that satisfies the equations of motion, if they're in the same refoliation orbit. So it's easier to see why this is not great for our purposes if we look at the Hamiltonian formalism. If I act with refoliations on a metric, on a 3 metric in the Hamiltonian formalism, this is what I mean by this delta, and here's the lapse, I would have something like of this form, and here you see it contains the extrinsic curvature, or it contains time derivatives of the metric. So it's leaving that initial slab, basically, or it requires information outside of that initial slab. One could say it doesn't depend solely on intrinsic fields at sigma, right? So I would try to look for possible symmetries that do maintain, do have an action that is intrinsic to these sigmas by demanding that they're linear in the momenta, right? Because then when I do a Poisson bracket with here, I will eliminate the momenta, and I'll have something that only depends on the metric H and on possible Lagrange fields. So this is the... And, you know, this is not working. And you can go on and you can try to look for them explicitly. You just take some trial ones. Here you have some general functionals of the metric and Ricci tensor and so on. And you see when they generate symmetries. And then you see in the sense that if they form first-class constraints. And at least up to 4th order, I think, is what I tried. I haven't proved this in all generality, but I think it's a solid conjecture. The first-class property implies any of these here. So first, I can take just no dependence on the metric and just have this as a Lagrange tensor field. And this would imply a constraint of the form of pi b equals 0. This is completely frozen. There's no dynamics there. So really no possibility of dynamics there. I don't want that. And another one is that there is a scalar Lagrange multiplier and the metric. This gives you the Weyl constraint, trace pi. Okay, this is called the Weyl constraint because, as Flavio said, and I think Julian as well, this would generate, upon the action of Poisson brackets, this would generate conformal transformations of your metric and of your momenta. And finally, we have, with one derivatives, we have the spatial diffeomorphisms, okay, which depends on a vector Lagrange multiplier. And I will try to switch slides with this until the end of the talk, I'm sure. And so, yeah, the more complicated ones, if you try something like this, they don't really close if you try to put them in there and try to see when they form first-class constraints. They don't really close. This is not entirely true. There's one exception, which is of this form. This does close. But this is something called the conformal Laplacian. It has covariant properties in the conformal transformations. This is invariant in the conformal transformations. So you can translate this using Yamabe classes and transforming this into constant ones. And depending on the Yamabe class, it will reduce to trace pi equals 0. Other Yamabe classes, I can't really say. So here's what we're getting to at this first part, is that by demanding law of the instant in metric variables, so having this transfer matrix picture and demanding that my symmetries will just shift things around in these two surfaces, this already suggests that the conformal geometrodynamic or the kinematical degrees of freedom are the real physical degrees of freedom. Okay, and this is what I was referring to when I said that, yes, maybe I can still retain the same picture of syntactic safety, but maybe I'm not in the, or I could consider a different environment for it, a different theory space. Okay.
You're throwing away the Dirac algebra.
Sorry.
By just insisting on linearity.
That's true. Yes, that's right. The Dirac algebra, as you know, it's an algebroid, right? As well. It depends on the field point.
You call it, but it's called the Dirac algebra.
That's right. I am. That's right. Yes, I am. Yeah, I'm just mentioning that because that is well, we'll see. It will be kind of pertinent here. So if I start from a general, so here's a general type of Lagrangian, or an initial general type of Lagrangian that I could have that obeys. Let's at least think first about the time-independent symmetry transformations. Okay. So for the time-independent symmetry transformations, I have. So wait, let me just. How much time do I have?
More than 15 minutes.
That's not great. More than 15. Okay. Okay, I'm about halfway there. Okay, so good. So here, these tensors here are Cotton tensors. I don't think they have been mentioned before in this conference yet, but they are obtained actually from metric variations of the Chern-Simons functional when you write it in terms of the Levi-Civita 1 form. Okay, and they have very interesting properties because they're obtained from a variation of a Chern-Simons functional. They are both traceless and divergenceless, and they have covariant conformal transformation properties. So they transform with a definite weight that doesn't depend on derivatives of the conformal weight under which you transform them. And here you can put as many as you want of them. Each one will come with their own coefficient, but they have to come with some fractional power. And they have to be here in order to cancel a conformal transformation of H. Remember, I want to make this conformally invariant. Okay, so when I perform a conformal transformation, square root of H will transform. This will not transform if I'm talking about still about transformations that don't depend on time. And so I need something here that will cancel out the transformation from this, and this is the object that you can write down. And you have a separate one with a bunch of cosmological constants, and you have a general functional of the Chern-Simons general function of the anyways. And so we can let's take the simplest one. This is the simplest one, and so here. You can already, so here, first of all, I want to say that this is kind of like an energy functional in the space of three metrics, right? You can see, I will talk a little bit about this as we will see. This forms the role of a supermetric. But for now, I still haven't faced the problem that I have only defined constant in time gauge transformations. Upon non-constant gauge transformations, for example, diffeomorphisms that depend on time, for which it's the identity at t equals 0 and its flow is given by psi, the H dot will transform in this form, and it acquires this Lie derivative, as we know. Now the idea of this is to add, as we do in usual gauge theories, when you have these non-constant gauge transformations, you can add a connection that will cancel this non-covariance of the gauge transformations. Yes? No, because that won't be. Because of square root of H here, this will transform. This has a conformal weight. It will transform. If you transform the metric as e to the 4 phi, this will transform as e to the 6 phi, and this doesn't transform. So without this thing here will be conformally covariant. That's true. But it won't be conformally invariant. Okay, so here's one point: is that under this type of diffeomorphism and conformal transformations, my field space for this theory, which is Reen, forms a, basically, there are some issues, but basically a principal fiber bundle picture. Okay, and this is the point that I was saying, that it's not a groupoid, and the projection onto the base space here, the projection along the fibers here, is independent of where I take on these fibers. It's not a, well, it's independent of the orbit point, and there's a straightforward equivalence relation between these orbits. And now what I was saying is that, okay, but if I vary the gauge transformation from orbit to orbit, I will acquire this other term that is not really covariant with respect to the gauge transformations. So I want to add a connection that will covariantize this. And it's not very hard to do, in fact. I'm using this metric here on this superspace, or this configuration space. And you can correct this to basically something, this is usually how a connection is described in this principal fiber bundle picture. You basically just subtract, if you have a velocity here, you subtract how much it deviated onto the vertical direction. Okay, because I have a supermetric, I can tell you what is a component of a velocity that is vertical. And then I can just take that away and have, so this is the horizontal projection of H dot. And because this is a definite metric, unlike the DeWitt metric, for example, because this is a definite supermetric, you can show that you actually, barring the existence of conformal killing vector fields, you have a well-defined projection, orthogonal projection. Okay, so this is what I was saying. You can correct that to that. And the correction is, you can write v hat. Here I already took the traceless part of H dot, because part of the correction will be just to take the trace part out of the velocities. And this psi, this vector field will be a linear functional on H dot, as it should be as a connection. It acts as a linear functional on the velocities of the trajectories. And it's defined by this, so it's sourced by this, and it's defined by this equation here. And it's the vertical projection with respect to the conformal diffeomorphism covariant metric that I wrote down before. Okay, so basically what I'm saying here is, look, if you can take a path here, and if you choose a point along here, there's a unique horizontal lift of this point, of this curve, I'm sorry, right? So I can write an action in this full space here that will correspond to an action in the base space by choosing something that I know will be a horizontal lift once I have chosen an initial point. And this is what characterizes a horizontal lift, if it's satisfied everywhere. Okay, so now we're getting to the closure of this second part. What I have presented here is looking at this different symmetry principles that I want to act in slabs. I was led to particular ones, basically conformal diffeomorphisms, which are the symmetry principles of shape dynamics, which were arrived at by different means, by more thinking about relational concepts. And here the action functional is a conformal diffeoinvariant energy function in Riem. So there are some issues here because you could have done it as a geodesic functional if you have taken a global square root, but I would have just gone to the arc length parametrization as a gauge fixing. So keep that in mind, but that's not really important. And the extremal paths are arc length parametrized geodesics for this metric. So usually for a path integral, you just have a gauge fixing section, right? So you just take something, you take a whole surface that will cut through that big configuration space, that will have one representative for each point in base space. Here I did something slightly different. I'm taking a path integral picture, and so for each path, my gauge fixing is actually, I choose an initial point, and for each path, it gauge fixes the velocity of that path to be horizontally propagated. So each path is only represented once you have chosen the initial point. And then there's this special gauge fixing that basically says, because you see here I could still choose anything because I have a horizontal projection, it would always project to the same thing. But if I choose a gauge fixing for the velocities that says I've actually started with the one on which the vertical projection is just the identity, it turns out that the Popov determinant cancels with the functional delta coming from the horizontal projection. This is, okay, I need to run a little bit. I only have 10 minutes. And there's also something about coupling to matter, something that Flavio mentioned because of the conformal weights, the Young-Mills derivative, the Young-Mills action emerges naturally. But here's the most important point of this part, is that I can explicitly maintain that action, that general action that I showed you. I can explicitly maintain a general Lagrangian that is quadratic in time derivatives and has two transverse traceless momentum degrees of freedom. Okay, so this is somewhat, maybe it has nothing to do with reality, at least this naive one that I've shown you, probably doesn't. But as a principle, I think it might be interesting because, for instance, Rojava-Lifshitz has certain problems with the number of degrees of freedom, scalar gravitons, and so on. Other theories might not maintain the number of time derivatives that you have on the theory. In this one, you have a nice theory space in which you can have both of these features. Okay, so if I had an alternative explanation just of space-time, of curved space-time, I would say that conformal and invariant degrees of freedom evolve together in the sense that everything is evolving together with the matter degrees of freedom. You don't think of in a certain sense, you don't think of the background first and then put things on there. Time is derived from change in physical degrees of freedom. Tim is going to talk about both of these things, so I might leave it for later. And you can also think about the equivalence principle as local symmetry transformations to be used along the evolution of weakly back-reacting source, so that the first approximation, the trajectories will behave as evolving in a homogeneous vacuum solution. And Steve and I have a paper discussing this for shape dynamics. Okay, so this is the more maybe polemic or controversial part of the talk. So be gentle. No, I'm kidding. Go ahead and rip me. But so let's go back to that original transfer matrix, right? Here I'm only thinking about relational configuration space. So there's no time. There's no variable specific for time. I'm just thinking of configuration space where all these these spatial metrics exist, or spatial configurations, whatever.
Configuration space is free or conformal?
Yes, good. So here I was going to ignore symmetries. So, but you should think of it as conformal superspace. So in relational quantum mechanics, you can, people have already thought about this, that you can look at the passage of time as only told by the relations of things. And there are some nice actual implementations of this for particle quantum mechanics in terms of, for instance, partial observables. So you have this transfer matrix, and you have a projector here that integrates over all times for the Hamiltonian evolution. But what will interest me most, actually, is this representation in the path integral by Xu. I don't know how to pronounce his name. And here, this is the classical action along gamma bar. Gamma bar is a path in phase space, but it will project down to a path in configuration space, which is parametrized curve between the 2 points in configuration space that I have. So basically what I'm doing here is I'm taking all actions over paths, not classical, forget classical, I shouldn't have said that. And they're on the constraint surface here, the Hamiltonian constraint surface. He showed that original representation by other people for relational quantum mechanics was equivalent to this path integral one. And you can also make this work if you have compact Lie groups by doing group averaging. Here, so the interesting thing that he showed is that if you have a deparametrizable system, so basically a system in which you can globally separate degrees of freedom between some kind of variable and some other variable that will work as time. And there's some other condition for it to be completely parameterizable, so the Hamiltonians at different times have to commute and so on, but let's not focus on that. T here has no special ontological status yet, okay? It's just part of the configuration. But it's just, yes, 5? Okay. This didn't help. Okay. Yeah. So, so this transfer matrix represents the amplitude related to measuring Q2, given that Q1 was measured at a previous instant. This is a sentence of Xu. But I'm in the quantum mechanical purely relational setting. What does the word previous here mean? You don't have this this possibilist time. So the previous instance here implies this possibilism, implies that there is something that had happened before. But I don't really need this. I only need nowism. I want to relate the amplitude to relate two nows. Okay? But for that, what I want to do, I want to define a wave function over my whole configuration space. And to do that, I will fix one absolute configuration, one absolute now, let's say. And I will define the wave function over all of configuration space as this transfer matrix from that, let's call it the vacuum, or Q star, to the given configuration where I'm at. Still timeless, but I have something that I'm going to put there and fix that as absolute or primary. So this, as I said, will give enough structure to extract a more complete notion of history. And the interesting thing is that for a metric theory, conformal superspace forms a stratified manifold with corners of different dimensionalities. I don't really have time to tell you about this, but it's, it has different strata, different dimensions of manifolds that you form once you project this down. And you have different corners that correspond to different degrees of homogeneity of the metrics under which you're projecting them. And there's a least dimensional one that is the corner of corners, let's say. It's, and that is a natural point to set a boundary condition in. Okay, and this is work by Fisher in 77. This is the mathematical formulation of what I'm saying. And it turns out that for Riem over S3, if I'm talking about the 3-sphere, there's a single such configuration that projects down to this corners of corners, the corniest of corners. And that's the round metric, okay, in Q star. This is if I don't allow degenerate metrics. If I do allow degenerate metrics, then the metric that is the most homogeneous is the vacuum, the completely degenerate one, the one that has no structure. It's just a point. Okay, so quickly. But perhaps now the interesting thing is that there are certain circumstances in which aspects of Q1 exist embedded in Q2, records of Q1 inside Q2. So even if I don't have time, if I have some wave function over my configuration space, I will have some way of identifying Q1 as embedded, or aspects of Q1 embedded in Q2. And this is a simplified definition of records where a configuration Q2 will have a semi-classical record of Q1 if all extremal paths, all classical paths that interpolate between the preferred configuration and Q2 will, for some time, for each path, for each of these extremal paths, go through Q1. Okay, I will draw that for you very soon. Well, I don't have very soon, but and so there's a coarse-grained version of this in which I need to talk about what kind of degrees of freedom am I taking into account, and how fat do I need to take the amount of paths that I'm including on around each one of these extremal histories that seed them, and in principle they are related to the Planck length, and there is a specific way in which they are, specifically in this case of theories that are given by geodesics. The radius of these are given by radius in this supermetric, and they're just so that it actually communicates the whole amplitude up to h bar. Okay, but what I'm saying is, so here, this would be the record, okay? All the extremal paths are going through this point, and this is the final point, and I'm saying phi r is a record configuration of phi. That's the initial configuration. And then you can show that when this is the case, even if you don't have time, and I don't have time apparently, but that's the amplitude actually decomposes, it factorizes. And this is the interesting thing, okay? So that the amplitude at Q will factorize between the amplitude at Q1 of its record and the amplitude to go from Q1 to Q2. I'm not going to show any of this. But if you have more than one record, and then there are certain conditions in which you have nested records, records of records. Okay. And then you can do some things to actually get, I want to define some way to count configurations. I have the amplitude, and I want to some density over configuration space. And this is what and you can kind of not really derive, but have almost a derivation of the Born rule, that this density should be given by the Born rule on configuration space. We can talk about this later. This comes from the semi-classical approximation, and when there's no interference. Okay, so this is I'm almost getting to the end, but then okay. So from the semi-classical approximations, I will have certain configurations that actually are connected by extremal paths between this preferred configuration and now. So configurations like now, which I think of as having a classical history between now and, let's say, and Big Bang or whatever it is that you think is this initial configuration that you have. And they will tend to have concentrated amplitudes on them around these extremal paths, just because of the semi-classical approximation, because we're so far away from these Q star that the semi-classical approximation holds, because the action is so much greater than h bar. So the ream is unordered. It's like grains of sand on a beach, but the path integral will automatically focus the amplitude along extremal trajectories. It's like drawing these lines. It's like the wind drawing the lines of sand on the beach. And this is this is the more polemic part. I have no proof of this. So records will tend to form for these trajectories. And for chaotic systems, extremal trajectories do fan out, right? This is a property of chaotic systems, is that if you just look at configuration space, the trajectories, they disperse, basically. They fan out. This is given by Lyapunov exponents and things like that. And my question here is, generically, if you take these extremal paths that are much larger than h bar, is it true that you would usually only have one extremal history between these 2 points because they have all diverged away? I don't know. This is a question. And then the amplitude for these points will actually factorize as a continuous history, as we think of it, and become conditional probabilities. And this is the main point. This is the point of that Born rule and how it acted on the amplitudes. Is that this volume form that I define in configuration space will have this very interesting property that it factorizes for a record. So it's as if a record had occurred, even though there's no time, because the amplitude has factorized between this and a conditional amplitude on Q1. On Q1 is the record. And this is basically what happens in the Mott bubble chamber experiment, okay? So this would be one configuration. Let's just think of one of these lines. The Mott bubble chamber experiment, very quickly, is you have some alpha decay particles. It's a precursor of particle detectors, accelerator detectors. And you have some gas here, and when the alpha particle comes out, it condenses the gas along it. And you can actually get some sense of history. Julian is really an expert on these things. You can ask him about it. And what I'm saying here is that, look, if you take a configuration like this is, let's say, P of Q. You shouldn't think of PQ just as, one shouldn't confuse physical space with configuration space, okay? So configuration space is one, let's say, for which you have the whole line.
And I'm saying that the density or the probability density for this factorizes the probability density that you had this configuration here and a little bit down times a conditional probability of this and this. So in this sense, for the existence of this whole thing to happen, you have had the existence of half of it to happen or something like that. So you have this build-up, this nesting of conditional probabilities of which I'm calling, you can build up a history with it. I'm almost done. So then there's some notion of decoherence, and here I just want to show you very quickly. If I don't have chalk, and I don't have time. But so, okay.
I was just about to ask you, the previous slide, there's a presupposition, right? You just talk about conditional probabilities with no regard to decoherence.
That's right. That's right.
Well, it's already decoherent.
Yes.
For you to even talk about that.
Exactly. So that's very good. So that brings me to the slide very conveniently. I would have never guessed that. Like Indiana Jones. All right. So so you're absolutely right. And this is so in this picture. So let's look at this experiment. This is the non-destructive measurement experiment. Is you put a bomb in one of the arms of the interferometer, and even if the bomb doesn't explode, right, you don't see interference anymore. And this is not at all puzzling. It's only puzzling if you actually look on physical space, because then you think, well, the trajectories of the particles are meeting on C or D, but the bomb is not exploding. How's it detecting it? But in fact, if you look at it in configuration space, suppose you don't have the bomb there, then you have two trajectories, two extremal trajectories, and they finish at the same configuration. They start at the same initial configuration, they finish at the same initial configuration. If you have the bomb there, and if you have this many worlds picture where the whole ream exists, then in fact this other configuration for an extremal path, it will end in a this other extremal path will end in a vastly different configuration where a bomb has exploded, right? The whole configuration here is very different from this one, the extremal one, and there's no interference. And this is what in consistent histories, when you don't have interference between paths that have or coarse grainings that have similar amplitudes. When you don't have that interference, then you say that these coarse grainings have decohered. This is what you use the decoherence functional for that. And here I have these preferred coarse grainings, at least for paths that have large action compared to H bar, which are seeded along extremal paths. And this is the kind of thing that I explain exactly. And you only can I use this fact to derive this Born-Rowan, this probability. Okay, I'm not going to talk about locality. So, okay, so I started with some possible issues with the notion of GR time in quantum mechanics. And the main idea there was that the superposition of causal structures might be problematic. And then I proposed that in the transfer matrix, I implement symmetries that only acted intrinsically on the in and out.